Hello, everyone. Come on in. Before we get started, anybody have any questions? Got a couple minutes still waiting for people to come in. And then you had your test today. I hope that went well.
Yeah, Mr. Younger, I have a question. So, since I won't be back until next week, like, what can I do for I guess like a practice test since that would have closed today?
I'll go ahead and reopen it for you, and you
Okay.
can keep on doing it. You're going to be back what, next week?
Yeah, I'm gonna be back next Monday. I can probably take it Monday.
Okay, I'll set it up in the testing center for you to take it. What I'll do is I'll make it anytime Monday or Tuesday at any testing center on campus, or any TCC campus testing center.
Okay.
Send me an email probably Sunday if you can remember to, so I'll remember to do it, or actually Friday might be better. That way I don't, wait too long.
Okay.
Anybody else have any questions? Anyone? Got more people coming in. Woohoo! Okay. So last time we finished up chapter 7. Essentially, there's something else I'd like to cover in chapter 7, and that's actually a more realistic potential energy, gravitational potential energy specifically. So last time I did the work done in lifting an object, a height h, but I was doing it super slow, so that at every point the forces were in equilibrium, but just a little bit out. So what that meant was I'd lift up a mass that had a mass of m and a weight, therefore, of m times g. And if I applied a force just infinitesimally bigger than mg, it would move up, but not necessarily gain any speed. That's what I was trying to do. And I keep doing that. It might take 14 years to get up 2 meters, but basically it'll go up 2 meters, or h. And in doing so, that work, since the force was this way, the force of gravity was this way, our force applied was this way, and the displacement went up as well. So they're actually parallel. And in fact, the force didn't change. So I didn't really have to do work equals the integral of F dot dl. I just needed to do force, which is mg, times d, which in that case happened to be h. Okay. So I did that, and I found a potential energy, because remember, the work you put into a system can be converted to potential energy. That, for instance, anytime you take a book and put it up on a shelf, you're taking your work, integral of F dot dl, applying it to the book, and then sticking on a shelf, which now that book has the potential energy given by mgh. That's all well and good as long as the force stays a constant, but we already learned in the chapter on gravity that the force, which is our weight, is actually due to gravity. And that gravity force is g m1 m2 over r squared. So clearly, the farther you get from the surface of the earth, the smaller the actual force gets. If you're dealing with distances that are comparable to the radius of the earth, that can be a big deal. But if you're dealing with distances that are way infinitesimally small, when dealing with the radius of the earth, then you pretty much can ignore it for most problems. So, for instance, you'll look in this week's module and you'll see there's an extra credit problem. And what you can do is you can actually calculate using the fact that the weight is equal to gravitational force. So you'd say weight, W, is equal to G times, let's say, your mass, M, times the mass of the Earth, divided by essentially the radius of the Earth squared, because even if you're on top of a hill, the distance between the bottom of the hill and the top of the hill is infinitesimal compared to the radius of the Earth. In fact, I tell students this often. If you took the Marianas Trench and pulled it on the Earth, and you took Mount Everest and you pulled it on the Earth right next to each other, that distance from the top of Mount Everest to the bottom of the Marianas Trench is actually smaller compared to the radius of the Earth than the distance between the little black grooves on a basketball to the top of a pimple on a basketball. You know, those little nipples or pimples they got on there. That distance is actually a larger fraction of the radius of the basketball than Mount Everest is to Marianas Trench is to the radius of the Earth. So one of the extra credit points I gave you was calculate G. I suggest you do it, of course, just for the fact that GM, where M is the little m is your mass, big M is the mass of the planet over R squared, where R is the radius of the planet. That's equal to W, but W is also equal to your mass, M, times G. So solve that for G, and you'll see that when you use G, the mass of the Earth, because the little m's cancel out, G, the mass of the Earth, and then divide that by the square of the average radius of the Earth, you're going to get about 9.80. All right, so that's something you should do just to verify, one, that the units work, but also that you get 9.80. Okay, that's not the extra credit part. I don't require you to do that. But what I am wanting you to do for the extra credit part is I want you to calculate the gravitational acceleration at the bottom of the Marianas Trench. In other words, you're going to have to Google deepest spot in the ocean, and I'm assuming it's still the Marianas Trench, and find out what that depth is, and then subtract that depth from the radius of the Earth, and then calculate G there. And then do the same thing for the top of Mount Everest. So I'm assuming still, and I'm pretty sure about this one, the height of Mount Everest is still the highest point on Earth. However, it did change. I think it used to be 25,032 feet or something like that. That's what I seem to remember from reading Into Thin Air. But it changed on the order of meters from a recent earthquake. And of course, it always changes from earthquakes. But you're going to take that and add that to the radius of the Earth and calculate G for there. And what I want you to then do is do a percent error or a percent difference, between 9.8 and G at Mount Everest, and then a percent difference between 9.8 and G at the bottom of the Marianas Trench. Okay, so that's 2/3 of an actual extra credit problem. The other third, I can't remember right now, but I wrote it in the document, so you can look at it anyways. All right. So now what we're going to go ahead.
Oh, sorry. I thought I maybe misheard you, but did you say we take the depth of the Mariana Trench and subtract that from Earth's radius? Because that wouldn't make sense. Or do you subtract it, not add it?
No, you do subtract it. Yeah, for the Mariana Trench, you subtract it, and for the Mount Everest, you add it.
I spoke backwards. I'm sorry.
Oh, okay, gotcha. Yeah, I might have spoke backwards too, because I'm old, I'm crazy. I had a cardiac incident.
I feel the same.
And the older we get, the worse our memory gets. It's so bad. It's cruel. All right. Anybody else have any questions on that? All right. So what we're going to do now is I'm going to derive a potential that is consistent with gravity actually changing as a function of distance from the center of the Earth. Okay. So I'm going to do that. And then I'm going to consider tell you about a neat case that happens to work out, that happens to be exactly correct. Even though it was done with Newtonian physics, it happens to be exactly correct with relativity. In other words, general relativity, which is the version of relativity that Einstein wrote second, which was his desire to understand gravity in a more comprehensive way. And literally just in September of 2015 was had two major predictions finally bear it out, namely the existence of black holes, the existence of gravitational radiation and gravity waves. So that's pretty cool. All right. So anybody have any questions before I get started on that? Okay. So I'm going to open up my iPad and making sure my tip is screwed on, because my students taught me that evidently it's important for that little thing to be screwed on. So I'm going to share my screen with you. And I'm going to do that and say share. And then I'm going to click on this, bada bing, bada boom. And now I am mirroring. Okay, so what we do is we say that the change in potential energy, delta U, which, remember, anytime you see that triangle there, that delta U is equal to U final minus U initial. That's what delta always means for us, okay? Now, what we're saying is that's going to be equal to the work that we put in, which is also equal to the integral of F dot dl. And I talked to you about the importance of that integral actually being a line or a path integral. That's two different words for the same thing. Okay, so what I'm going to imagine is the Earth. Aha, I thought I could do that. Y'all see what I just did? I just held my pen on it. It turned it into a circle. Ha, I'm awesome now. Okay, so this is the radius of the Earth, which the symbol for that is circle. Okay, don't do it once I take my pen off, with that plus symbol in it. Okay, so that's the radius of the Earth. What I'm going to imagine is taking an object of mass m from one Earth radii out. Now I could call this horizontal line, I could call that the x-axis, but really you're going to eventually start to use coordinate systems other than x, y. You'll use polar coordinates. Hopefully you've already seen those a little bit, maybe in pre-calculus, but you'll definitely see them by Calc 3. But polar coordinates are cylindrical coordinates, which is polar coordinates with a z-axis, and then spherical coordinates, which is quite different, but they're on my YouTube channel if you want to. So all I'm saying is I'm going to use a symbol called r hat instead of a symbol called x hat or j hat or y hat. Okay, so I'm going to imagine basically all the lines coming from the origin of our coordinate system. Okay, this one coming out would be the x-axis. This one coming in, coming here would be the y-axis, and this one right here would be the z-axis, and they have to be a right-handed coordinate system. What I'm going to do is imagine taking that mass and carrying it out a really far distance, and it actually is going out to infinity. I do not like that infinity. That was a very bothersome infinity. Okay, and that was not much better. But anyways, that's what I'm going to do. Okay, so what I'm going to say is Newton's law of gravity as a vector, since the origin is actually at the origin of the coordinate, is actually at the center of the sphere, it's going to be g times the mass m of the object I'm moving times the mass of the Earth divided by r squared. But notice, if that was the y-axis, it would be pointing in the negative y direction. I'm going to say it's the r hat direction instead of the j hat direction. And there's no loss in generality there. I'm just doing that because that's the normal variable to do. And I'm slowly trying to steep you into the idea of different coordinate systems because it's going to come in real handy in the 242 course. Okay, so r hat vector is just a vector that no matter where you are in space, let's say this point right here, if you draw a line from the origin to that point, that line will be actually parallel to r hat. And in fact, if you take r, the vector that points from the origin to there, that would actually be the r vector we're talking about. And if you divide it by its magnitude, then you'd get not r, but r hat. The hat is the universal symbol in most places for a unit vector. That's all. Okay. Now, the fact that that always points from the radial, from the center out to a point, that means it's always going to point out. So that's why I got a negative in front of that, because I got to have it point in, because that's which way gravity is going to pull that mass in. Now, my path, I'm actually going to ride right along this axis that I've been treating as if it's a y-axis, right? But I'm going to now call it like the r-axis. So I'll say dl in my formula is going to be dr r hat. I am going in the positive r direction, so I've used the dl to indicate the direction I'm going. That means my range of integration just has to be from low coordinate r to high coordinate r. That way I don't double up and get the wrong sign. So delta u is equal to negative integral of g m mass of the Earth over r squared r hat dotted with dr r hat again. Again, no big deal about these r's. You could just say I'm going to keep it along the x-axis, because you're free to put the x-axis anywhere you wanted, or you can say it's going along the y-axis or the k-axis. Doesn't matter. You still have the same thing. You just have I hat and dx instead of dr. Okay, now I can also pull these constants out in front, and I'll get negative g m m integral dr over r squared r hat dot r hat. Sorry about that fitting in there. That was really ugly. Let me rewrite it just to not make it look so bad. Whoa. Okay, that's going to be equal to negative g m mass of the earth 2 times the integral of dr over r squared. So what I just did was I pulled that dr right there. I pulled that straight out from between the dot products. The dot products are what we call a linear operator. So I can take sums and multiplications and just pull them out in front. That's all I did there. And that left the r hat dot r hat after it. But we know from our formula for dot product, A dot B is equal to A B cosine of the angle between them. That means 1 times 1 times cosine of 0, because they're identical vectors. So clearly I'm just going to get 1 for that. Everybody follow that? Now I am supposed to integrate this from small r coordinate, because I already chose the dl to point in the direction of travel. So I'm going to go from small coordinate, which is the radius of the earth, to large coordinate, which is infinity. You can see automatically that the integral of dr r to the negative 2 is negative 1 over r. So that's going to get rid of that negative that I have here. That's going to become positive g m m over r, evaluated from r earth to infinity, which is going to be g m m. Now we have to take the limit as r approaches infinity of 1 over, actually I should do a little r there. And my limit looked ugly too. I'm going to rewrite that. Of 1 over r minus 1 over r that. Now that position could have been anywhere. I just happened to choose the surface of the earth. But in general, the result we're going to get is just for any r. Okay. But you see the limit as r approaches infinity of 1 over r is what?
Should be 0.
Exactly. So that's part 0. So what we ultimately get is negative g m m over r is the actual potential. Notice I dropped all symbols regarding the earth, because that's the general result. So if you're leaving any body of mass big M on the object mass little m, then the potential that you'll have will be negative g m m over r if you're a distance r away from big M center of mass. Okay, what we said was that was actually the final minus initial. And of course, the final, I think you can see, would have been, since it's infinitely far away, as r approached infinity, you'd end up getting 0 for the u. So the final energy was in fact 0. The initial energy was in fact higher, or a larger quantity than 0. But because of the way our coordinate system is, that ended up giving it a negative potential energy. So this is the only time I'm going to give you a conservation of energy equation that we use. And it's only if you're using this that you ever get a negative in my version of the conservation of energy equation. Okay. So that's the correct potential to use if you're dealing with objects moving from the surface of the earth, but or any other planet for that matter. But they're moving in such large distances that the distance is comparable to the radius of the planet, then you have to use that instead of MGH. Does that make sense to everyone? So this is what we call gravitational potential. With that equation, by the way, you can set up the equation for energy in an orbit. And remember, Kepler's law said that, for instance, the first law said that the planets follow elliptical orbits with the sun at one focal point. There's nothing else special at the other focal point, by the way. And then the second law says that they sweep out equal areas in equal time, which showed us that the planet would actually speed up when it was closer to the sun, and it would slow down when it's farther from the sun. And I try to tell people is, though that's not what that particular law is applied to, it's consistent with the actual facts about planets. So if two planets are orbiting the same star, the one that has the closest orbit to that star will be going faster, just like the Earth is faster when it's closer to the sun than when it's farther from the sun. So again, the second law doesn't have anything to do with that. It's just consistent with it. So if you ever forget that, it's a little hard to tell without some work when you're thinking about Kepler's third law or Kepler's second law, because Kepler's second law doesn't even apply to it. And then the third of Kepler's laws are that the square of the period of the orbit is equal to the cube, or is proportional to the cube of the semi-major axis. But if we happen to use the very special units of year for the period and astronomical unit for the semi-major axis, we have one piece of data for our solar system that's super helpful, namely that the year is, the period is how long? Yeah, that's a good teaching moment there. How long is the period in years for the Earth to travel around one orbit? One orbit. Whee! Oh, I'm back. All right, let's ask a harder question. This might be easier. How many days?
If nobody else will take it, I guess I'll say 365, possibly.
Yes. And how many years is that?
1.
Yeah, so there you go. I think the people are just shy. That's all. I know they know these answers. So when you say t squared is proportional to a cubed, and you use years and you used astronomical units, then for the Earth, we get 1 squared is proportional. That's in years, of course. Now, does anybody know how large the orbit of the Earth is, at least its average distance between it and the sun, in astronomical units? Nora will help me out again. No,
I don't know this one.
Okay, this is something that you might have learned from grade school. It's okay if you didn't. I haven't taught it to you, but it's called the astronomical unit. In fact, they just used a symbol till they knew what that distance was when they were dealing with like Kepler's models and all that stuff. We ultimately were able to figure out what that distance was, and we defined that to be 1 astronomical unit. Astronomy is awesome because it's the oldest science. So in every realm of astronomy you're working in, they work with the very best unit you could work with. So for instance, if you're dealing with relativity, they use masses like solar masses and stuff like that. And then, you could talk about the radius of a black hole as a certain number of sun black holes, or the distance to a planet could be parsecs, because that's the distance that a planet or a star is away from us, such that its parallax angle is 1 arc second. So in our case, the Earth would give us 1 for A in astronomical units. So to make a proportionality into a constant, you just have to replace it with a constant, or excuse me, into an equals. You just have to replace proportionality with an equal sign and then put a K next to it. So what would that K have to be to make this true? 1 squared is equal to K times 1 cubed. I think I heard somebody say it, 1, right? And of course, the units would be years squared per astronomical unit cubed, but the main thing is 1. Okay, so that third law, if you're dealing with objects orbiting our sun, then that constant can just be 1. You can use years and astronomical units and everything comes out nice. In fact, when I derived this expression, I got a G and a 4 pi, or excuse me, a G and a pi, I think. 4 pi? Yeah, 4 pi. 4 pi squared over, in fact. So I had a G, a 4 pi squared, and a mass of the sun. And if you use year and astronomical units, the mass in there will automatically come out in solar masses. So you'll immediately find out, for instance, what that star's mass is in terms of our own star's mass. So now that I have that, when I see that third law, it's not obvious to me that the inner planet Mercury is actually going faster in its orbit than, say, the Earth, which is 2 planets farther back, right? But by recalling the second law and how that works, just knowing that it's consistent with that result, then you can say, oh yeah, Mercury's going to be going faster. Okay. All right. Now that we have that, I'm going to show you conservation of mechanical energy. So your book generally uses, a lot of books do this, and I try to use a different version that I use for my algebra-based physics as well as for my calculus-based physics. And it's a lot, it's more useful. It can be applied to all the other problems, but it also can apply to problems where energy is not conserved. So what they'll normally say in conservation of mechanical energy, your book will use this. It'll say the change in potential energy plus the change in kinetic energy is equal to 0. Well, you know, just because I recently told you, and I've told you throughout the whole semester, delta means final minus initial. So you could also interpret this as U final plus kinetic energy final is equal to U initial plus kinetic energy initial. So that's a little closer to the way I do it. And that's also a way that a lot of books do it. But these are only for when the forces are conservative. Okay. Well, there's a whole neat sidebar of vector mathematics that comes from this. So you can say F is a conservative force. That means it's a Republican. No, that's not what it means at all. I'm being funny. Okay. Conservative, in this case, is more like Jimmy Carter telling people to, you know, turn their air conditioners down a little bit because you're quote unquote conserving energy. But it's not even that really. It's more like a zero-sum game that I told you about before. It's more like, hey, I've got a fixed amount of energy and that's never going to disappear. So F is conservative. And it turns out from cool mathematics that if that's true, all the things I'm getting ready to write below it is also true. The test, or a common test for it being conservative, is something called the curl of F, also called the rotation of F. I call it the curl of F, is identically 0. See how I put 3 equals bars there instead of 2? That normally means defined as, and here I'm using to tell you, hey, this isn't that if I put in a certain X, Y, and Z, then I'll get 0 for it. This means for all X, Y, and Z, I get 0 for it. So if you find that's the case, then you know your force field is in fact a conservative force, okay? That also happens to be equivalent to, this is kind of neat, an integral from A to B of F dot DL. That's the work done, right? So the work done in going from A to B is equal to some function of B minus some function of A, and it's independent of the path chosen. Okay. In other words, when I took that mass M out to a distance R, I could have went around and around the planet, slowly let R get larger and larger and larger and larger and larger and larger, and then shot in a straight line all the way out to R equals infinity. And the change in potential energy would have been exactly the same. as long as the only force I'm dealing with, which happens to be gravity, was a conservative force. And if you want to test it, you can do that calculation I showed you above, which I'll explain more later, but you don't want to do that. It's not the funnest thing to do. It's nice exercise, but I'll tell you how to do it later. But yeah, we can say that the force of gravity is a conservative force, as is the electric force, as is the magnetic force. Well, there's another version too. So again, if any one of these are true, all of them are true. This one, we're going to use a neat symbol. Look at that, an integral with a circle on it. That's like a KISS integral or something, right? So what we're saying is the integral of f dot dl over a closed path is equal to 0. And I think that makes sense if you look at the line above it, because if it's a closed path, it's the integral from B to B or from A to A. And f of A minus f of A is clearly 0. So all that means is, like, if the Earth starts, right here and then goes in a complete orbit, then it's exactly in the same place it was. So the work done, the total work done in taking the Earth all the way around has to be equal to 0, which is what that integral says. Okay. Now, the coolest part of this, in my estimation, is, one, I get to show you this cool mathematical writing. The upside down means there exists a scalar function f such that, so that means such that f is equal to the negative gradient of the scalar function. And that, of course, could be a function of x, y, z, for instance. So what are these crazy upside down triangles I'm writing, which we mentioned a little bit before? So in this case right here, where I'm putting the star right now, I got to get used to that. Okay, that case right there, what we're doing is we're calculating a determinant. I'm going to switch colors here. We're going to calculate a determinant of a matrix, the top row of which is I hat, J hat, K hat. The second row is the partial with respect to X, but not actually acting on anything. It's called a vector operator. Partial with respect to Y and partial with respect to Z. And then the third row is the X component of F, the Y component of F, and the Z component of F. That's what that curl is. So you can see, if you wrote that gravitational force that I just wrote for you, let's say this one right here, to do that, all you'd have to do is, first off, realize that it's going to have an X component, that all of which is multiplied by negative GMM. And then the X component would also have X over the square root of X squared plus Y squared squared. And then the Y component would be Y over the square root of X squared plus Y squared plus Z squared squared. And then the Z component would be the same thing. So you can actually do it if you wanted. I'm not requiring you to. I'd probably give you some extra credit if you wanted to, but it's a good bit of work. But anyways, because that is 0, we have all these other things are true. And in fact, that last one might seem really foreign, right? But that's exactly the reason why I can say U is equal to MGH, or U is equal to negative GMM over R. So the whole reason we can do conservation of energy problems is because all of this is true. There's actually another point you could do. If you've had differential equations, you've learned about exact differential equations, and that's normally written like some crazy function of X and Y and Z in front of dx, plus some other crazy function of X, Y, and Z in front of dy, plus some other crazy function of X, Y, and Z in front of dx, and all that's equal to 0. And in your differential equation class, you take the derivative of the one in front of x with respect to y. Actually, let's reduce it and get rid of the z completely. You take the derivative of the one in front of the x with respect to y, and you take the derivative of the one in front of dy with respect to x. And if they're equal, you know it's exact. Well, that also falls out of this too. I'm not going to go into details of that because that's, even further far afield than this was. So anyways, now that we have that idea, I can tell you that is why we have conservation of mechanical energy, because the gravitational force is a conservative force. Okay. And I've told you two others, the magnetic force and the Coulomb or electrical force is another one. So that works out really nice. Now that we have that and you have some understanding of what we're talking about in conservation of mechanical energy, I'm going to use that potential to consider a very specific problem. Let's imagine that we have a planet of mass big M and radius big R, and I want to escape that planet. I want to take off from that planet so fast, and I'm imagining this is like a ballistic missile, not a cruise missile. This is a ballistic missile, one that leaves with exactly the speed we need, and I want it to be so fast that it allows us to reach all the way out to infinity, but just comes to a stop right then. If it's actually having an additional speed, I'm going to have to go even faster. Okay, so I'm sort of choosing the minimum amount. So here's my problem. I'm going to write a circle, and I'm going to write a radius r, and then I'm going to imagine an object of mass m right here. The planet has a mass big M, and I'm going to shoot this off such that I have V initial right here, and that's what we're trying to solve for, sort of. And I'm just going to reach out to infinity, and V final is going to be equal to 0. Okay. According to conservation of mechanical energy, we could say U final minus U initial plus K final minus K initial. That's another way of just writing, like I told you earlier. You can write it as delta, or you can write it as the two on opposite sides. We're saying that equals 0. So what I'll do now is I'll say U final plus K final is equal to U initial plus K initial. But I'm going to choose that at infinitely far away, the potential energy is 0 and the kinetic energy is 0. So that's going to give me negative G M M over R squared plus 1/2 mv squared is equal to 0. Okay. So if you wanted to calculate the escape velocity of the planet, that would be what you do. So V escape is, you can see that you basically put them on opposite sides of each other. That negative will become positive, and I'm going to get the masses canceling out, and I'll get V is equal to the positive square root of 2g mass of the planet over the radius of the planet squared square root. That is the escape velocity. Okay. So in some sense, that's the only velocity you need to reach. So if we were, instead of putting astronauts or pilots of the space shuttle or whatever, instead of putting them in a ship that has constant thrusters going for minutes on end, we could just fire them out of a gun so that they leave the gun immediately with the speed they need. You could probably see some downsides to that, just physically speaking, right? Rapid acceleration like that, whether you're speeding up or slowing down, is just going to make you a puddle of goo in a chair. Okay, so we don't do it that way, but in principle you could, and we could do satellites that way. That wouldn't be a problem. Now, what I'm going to do is imagine a planet that's so massive that only something moving at the speed of light could come close to even escaping it. And in fact, it won't escape it. That thing is called a black hole. it implies the M is so large / R is so small that V escape is greater than c, the speed of light. Okay. Well, if we do that scenario, then I can calculate the radius. And what I'm going to get is negative g m over r squared. Excuse me, r. Both of those are not supposed to be squared, by the way. Nobody caught me on that. I'm sorry. Everybody remember your potential has r to the 1 power in the bottom, not r squared. So that was a boo-boo on my behalf. Not like I ever make them, right? Okay. So, whoa, still got my eraser there, Billy. Thank you. Okay. Plus the kinetic energy is going to be 1/2 mc squared. All that equals 0. So now you can see, in fact, let me correct this too. Remember, I had a square down there. That r is just supposed to be r, not r squared. So everybody make those corrections. That was me using the gravitational force instead of the gravitational potential energy. So when I solve for r with a pen instead of an eraser, I get r is equal to 2 gm over r, or excuse me, 2 gm over c squared, because the m's will cancel out. You can see that, right? So 2 gm over c squared, take the square root. Oop, don't even have to take square root. Sorry. There I go again. Two gm over c squared. Come to find out, we just did this with classical Newtonian relativity, okay, or Newtonian gravity, I should say. It turns out that is actually the event horizon distance for a black hole when we actually use Einstein's field equations instead of, Newton's laws of gravity. So in fact, that is theoretically correct. When my other finger comes up here, it causes problems. So your extra credit problem, remember I elucidated 2 cases already where you're going to calculate gravitational acceleration 9.80 at the bottom of the Marianas Trench, and then again at the top of Mount Everest, whatever the highest and lowest points on the Earth are. The third part, and you're going to calculate the percent differences. The fourth part then is this. I want you to calculate R black hole for Earth. Okay. And I want you to calculate R black hole for the sun. Okay. Now, what I mean by that is I want you to calculate it in meters, times 10 to whatever power you need to, but also find a more useful unit, like a unit like maybe a kilometer will be helpful, maybe a megameter will be helpful, or something like that. One where the number that you actually have to use is like somewhere between 1 and say 50. Okay, that's all explained in the extra credit link. But that's what you're going to do. You can plug in the formula for the mass of the Earth and the speed of light, which is 3.00 times 10 to the 8th meters per second. All these are also in the front cover of your book if you got a hard copy. If you got a print edition, you can find them there as well. Otherwise, you can find them on My Lab and Mastering has a section for it as well. Let me actually look at that while I'm here. I'm going to say access my e-text. When I go to your e-text, which I think all of you have access to, there's a section in the left-hand side called front matter, and you can click on that and it'll give you all those constants and stuff. Okay, so you can do that from your e-text within My Lab and Mastering. So the first page is just the title page, then it has front matter, Library of Congress, all that good stuff. Then it has the table of contents. Actually, maybe I have to go further on than this. Okay, let me double check. So the front matter, let's say answers to odd problems. No, let's say in papers. Let's see if it's got it in there. There it is. So the in papers has the constants that are on the front and back pages. So in papers is what you want to go to. I know you're not looking at my screen right now. I just was flipping through it since I had it open already. All right. Any questions about those extra credit problems I was just mentioning to you? And like I said, extra credit problems basically count as another homework assignment. So if I offer, for instance, 5 throughout the whole semester, and I already told you, say that I was going to drop your 1 lowest homework grade. If I offered 5, now I'm going to drop 6. So that's how that homework works. Any questions on this neat new potential energy formula? So what I was saying with that is now that you have that potential energy, you can set up the energy equation like conservation of energy, because there's no energy loss to friction and air resistance. Friction and air resistance is negligible in space, especially when you're dealing with things the size of planets and you're talking about space where there may be a couple hundred atoms per square meter or something like that. Actually, in the least dense parts of space is on the order of hundreds of particles in a cubic meter. Regular space is a little bit more denser than that, but the main thing is it's not going to matter very much. So you can set up that energy equation, and doing that, you can actually get the velocity of the planet as a function of distance away, r. So, and I don't just mean at aphelion and perihelion, I mean anywhere at all. And that's exactly how we do, for instance, a Hohmann transfer, which is an orbit that we would use, quote unquote, to save gas if we were going to Mars. So what we could do in principle, let me stop. Now I want to keep on sharing. Y'all can see my face. That's good enough. So what we're going to do is we're going to imagine a scenario in which you're sitting on the surface of the Earth. Sun finally sets. You look up and you can see Mars because you know Mars. You've seen it, every day this week, and you knew it was going to be in this constellation at this time of this year. So you look for it in that constellation. You see the star, quote unquote star, the bright spot that's out of place. That's clearly Mars. You say, okay, well, all I got to do is I'm going to take my rocket ship that's mounted vertically on the Earth. I'm laying on my back in a seat, and I'm going to hit the accelerator really, really hard. Take off, and I just keep steering, with my jets, keep steering so that I keep heading towards Mars no matter what. Obviously, I might run by asteroids, all sorts of stuff. Space is really empty, so I'm not going to see much of it, but their gravity is going to pull me a little bit off course. So I got to keep watching it by, using my steering wheel or whatever. And then finally I'll end up at Mars, and that would be really awesome. But the problem is we can't do that. Okay. That would take so much fuel that it would be cost prohibitive. For instance, this is like 1988 data, 1988, 1987. For every pound you sent to space in 1987, it would cost you the equivalent of a pound of gold. Now, a pound is like 16 ounces. And the last time I checked, an ounce of gold was worth about $1,400. So 1,400 times 16 is a buttload of money. And that's how much you have to pay per pound of weight. So obviously that would take a buttload of fuel. Not only that, the way travel in space works is just like the way you have to try to escape from the surface of a flat, frictionless pond. Have you ever thought about how would I escape from the surface of a flat, frictionless pond? People say friction, for instance, is that force that opposes motion. And it's correct to say that, but it's also the force that allows us to have motion. The reason why it's so hard to ride a bike on a frozen lake or to walk on a frozen smooth lake is because you don't have any friction. Normally what you do to walk is you sort of push back on the earth towards, if you're walking forward, you're going to push backwards on the earth. And because the earth has a friction acting between the surface of the earth and your foot, it's going to respond with Newton's third law by applying the exact same force to you in the positive direction. Well, if you're on a frictionless pond, there's no friction, so it can't do that at all. The only thing it's going to be able to do is match your up and down force, because that's all the ice can do. So how do you get off such a planet? Well, or such a plane? Well, one thing you can do is use the idea of conservation of momentum. Or another way of looking at it is Newton's third law of motion. Newton's third law of motion says for every action, there's equal but opposite reaction. What I really need is some force, like what I used to use was the friction between my shoe and the ground, that would push my foot and it would push my foot forward and allow me to fall forward such that I could catch myself with my other foot and then do the same thing. Well, I need a force applied to me in order for me to move that way. So the only thing I could really do is say, let's take off my parka or whatever my big coat is, okay? I'm going to take that off and I'm going to throw it the opposite direction I want to go. Because whatever force I applied to that parka, according to Newton's third law, is going to be applied back to me. Now I'm going to want to stomach pass it, because if I did it high, I'm just going to tend to flip over. So if I threw it like this, it would just cause me to tip over like that. So I want to throw it sort of in line with my center of mass, which would be right about my belly button height. And in that being the case, if I applied a force of 100 newtons to the parka, then it would move off with some acceleration given by that 100 newtons by the mass of the parka. Me, on the other hand, experiences the same force. And in fact, my acceleration would in fact be 100 newtons divided by 100 kilograms, because in a good day or a good year, that would be my mass. It's not that right now, but anyways, so I'm going to get a much smaller acceleration than the actual parka did. But the main thing is I now have an acceleration, and as long as it's not zero, I can coast. Since there's no friction, I can coast for the rest of the way out to the edge of the frozen pond. So that's how you move. Well, that's the same thing you got to do in space. In space, what they do is they throw a bunch of little coats, little gas particles that are sort of exploding, and they throw so many of them that it's a huge mass per second shooting out very, very fast from the back way. And then, of course, that actually results in a decent sized acceleration. That's why the tank, when you ever saw the space shuttle take off, it had a huge tank that was literally like 2 or 3 times the volume of the space station. Plus, it had 2 tanks on the side that were probably comparable to the volume of the space station, of the shuttle. So the best way to actually get to Mars is not gunning it. It's by taking enough fuel to do what you need to do. So how we do that? Well, what we'll do is we'll have the sun right here, and we're going to have Earth's orbit right here. And then we'll have Mars's orbit right here. Okay. So what I'm going to do is try to create an elliptical orbit. Remember, elliptical orbits have one long leg and one short leg, right? They've got a small, a semi-minor axis and a semi-major axis, which is also a minor axis and a major axis. So what I can do is set up an elliptical orbit where the perihelion distance, when I'm closest to the sun, is at the Earth, and the aphelion distance is where I'm at the orbit of Mars. Now all I got to do is take off from Earth and then calculate, for instance, how fast Earth is going, and then figure out how fast I need to go to make this orbit, because I need this orbit to be having the right speed when I'm close to the sun, so that I go so far away from the sun that I get to Mars's orbit. So I have to find out what that speed is. And then I've already got a little bit of free speed because the Earth is moving like that already. So I just take the difference between the Earth's velocity and the velocity that I need. And that's how much thruster I have to use. I use the thruster until it gets to that speed. And then I don't have to think about it. Gravity is just going to pull me around to the other side. Now, when I get to the other side, I'm going to be slowing down a lot, because that's the second law of Kepler, which says they sweep out equal areas in equal time. The long slice of the pizza is over there, so that has to be narrow. So when I get there, not only do I have to make sure Mars is there, so I got a planet where Mars is ahead of me in the orbit at exactly the right angle, And then I got to make sure I'm going the right speed to catch up with Mars. So again, I'd have to calculate Mars's velocity there and my velocity there, and then see what kind of thrust I'd have to give it to bring my ship up to that velocity. But again, you can all do that now because we have this nice little expression, GMM over just plain R, not R squared. Okay, that's called the Hohmann transfer. I have no idea. I'm going to say HOHMAN. And it might even be 2 N's. I don't know. But anyways, it's been a long time since I taught that material. But that is it actually happens to be a problem in the back. I think in the end of the chapter on gravity, potential energy, I think it happens to be in there. So you could see it if you want. If it's not, it's from another book. But either way, that's what another thing that potential gravitational potential allows us. So any questions on that? All right, so that was the last thing I wanted to do with regards to chapter 7. Now I'm going into chapter 8. Now, I technically already started chapter 8 when I set all these bullet points about conservation of energy, specifically this one right here, this one right here, this one right here, this one right here, this one right here. That was me starting off the chapter on conservation of energy, and the version of it that your book uses predominantly is that conservation of mechanical energy. So I wrote that up there, but now what I'm going to tell you I use is this, and I'm going to give you one sort of mother of all examples, and that should be enough to show you how to use each of the terms. And then, in fact, you're going to get enough examples in your textbook as well as in doing your homework to make sense of the rest. So conservation of energy is what we're talking about. And what I do is this. I say the work you put into the system plus the initial potential energy plus the initial kinetic energy is equal to the work that the system puts out plus the final potential energy plus the final kinetic energy plus I'll add another term, E loss. So this work in, work out, and E loss, I can actually have multiple ones. I can have work in 1, work in 2, work in 3. I could have work out 1, work out 2, work out 3. I could have E loss 1, E loss 2, E loss. The main thing is I want exactly one term for each phenomenon, and I only want one term. If I did twice, then I'd be counting some effect twice, and that's not good, right? But let me show you the example that I want to work with this. So now that you've seen it, my example is going to be this. So I have a father and his daughter on a hill, and the daughter's on a sled. Okay, got a little ponytail. All right, so the daughter's sitting on her sled, and the father is going to give her a push like this. Okay, so the mass of the girl and the sled is going to be 80.0 kilograms. The force the father puts will be 100.0 newtons. And he's going to do it for a distance of 3.00 meters. The height from here to here is going to be 100.0 meters. And then they're going to run into a friction full surface that is, let's say, X is equal to 20.0 meters. And the friction force there, F, is going to be, let's say, 30.0 newtons. And then they're going to run into a safety mechanism that's made of a spring. And the K for the spring is 1,000 newtons per meter. Okay. What I want to know is A, will the girl make it to the safety bumper? And if so, how fast will she be going? Okay. Part B, I will state again later, but I don't want to take up the room for it right now. I'm going to say how far is the spring compressed, assuming we actually, I've given big enough values to make the girl actually reach the bumper. Okay. So my equation is work in plus U initial plus kinetic energy initial is equal to work out plus U final plus kinetic energy final plus E loss. I'm going to call the E loss friction. I don't have to. I might even call that work out if I wanted to, because in some sense, the little girl is doing work by traversing, pushing a force through a distance of 20 meters, right? But in this case, I've chosen to call that friction. If I was going to go all the way to where the spring actually did catch her, then it would be E loss, and then work out would be 1/2 kx squared for the spring. This Wn is going to be by the father. Okay. The potential energy initial is going to be mgh. And here's the thing. So when the father pushes the little girl, she's going to gain a little bit of speed from that, or else he wouldn't be pushing her, right? But we're going to ignore that little bit, or just assume that it's so small compared to when she gets onto the actual slope that it's not going to matter. So in doing that, I'm going to say we have 100.0 newtons times 3.00 meters. That's the work in by the father, plus 80.0 kilograms times 9.80 meters per second times 100.0 meters. That's the mgh. The kinetic energy initial 0. The final potential energy is going to be 0. And the workout for this part is going to be 0. So I'm going to say the right-hand side is just equal to 1/2 times 80.0 kilograms times V squared. Okay. So I'm going to basically add this. This is clearly 300.0 joules. And that's actually carrying 1 extra sig fig. This 9.8 times 80 times 80 times 100 is equal to 78,400. And in fact, this and this are extra digits. And then over here, I get 40.0 kilograms times V squared. So if I add those two numbers, 300 plus the 78,400, I get 78,700 joules divided by 40.0 kilograms. Take the square root of that, and that'll give me V. So I'm going to take that 78,700. I'm going to divide it by 40. And I get 1,967.5. And that's meters squared per second squared, because a joule is a Newton meter, which is a kilogram meter squared per second squared. So now I'm going to take the square root of that, and I'm going to get 44.4 or 44.36 meters per second, carrying 1 extra sig fig. So yes, she will make it all the way to the bumper. And in fact, when she gets to the bumper, she's going to be going 44.36 meters per second, which I think is on the order of 100 miles per hour. So we're going to hope this is a little more pleasant than it sounds right now. Okay. So now for part B is how far will the bumper compress? Okay. So there's a couple ways you could look at it. You could write that whole equation again: work in plus U initial plus kinetic energy initial plus work out plus U final plus kinetic energy final plus E loss. Now, in that case, though, you would say work in is definitely a term. U initial is definitely a term. Kinetic energy initial is essentially 0. The work out will be 1/2 kx squared plus U final, which is going to be 0, plus kinetic energy final, which is going to be 0, because we're really allowing the spring to compress until it comes to a velocity of 0. And then plus friction force times what I call that, X. Okay. So you could do all that from the very beginning, but you can also just say, hey, wait a second. I know when she gets to that bumper, she has a kinetic energy given by 1/2 times 80.0 kilograms times 44.36 meters per second squared. And that's going to go into 1/2 kx squared. So that's what I'm going to do. I'm going to say 1/2 times 1,000 newtons per meter times x squared, which is what we're wanting to know, is equal to 1/2 times 80.0 kilograms times 44.36 meters per second. You see why I kept an extra sig fig squared. That gives me X is going to be equal to some god awfully unreasonably large number, but that's okay. We don't care. So I'm going to square that number times and then I'm going to divide by 1,000. And then I'm going to take the square root. And that gives me 12.5 meters. So that's how far that spring would be compressed. Any questions on that? So the advantage of that problem is that it uses the method that I suggested, and it actually addresses every possible term in there. And I've given you enough of an introduction, of course, for you to understand how you could use it for other problems. So all that's well and good. The other thing, though, is that really, because you saw, let's say in this page, remember this scalar potential right here? One thing I just hit erase. That was not what I meant to do. Let's get back to red so I can fill that in correctly. That looks okay as is. So let's go back to blue now. This right here tells us that we can use the potential energy. Okay. The fact that we can use that tells us something, because the potential energy, if you actually want to know the force, you're going to have to take something like the derivative, because that del operator we saw is that second line of that matrix up there. So you put an I hat to the left of the partial with respect to X, and then you leave a blank and you put a plus sign, and you put a J hat right next to the left of the partial with respect to Y, and then you leave a space and put a plus sign, and then you put a K hat next to partial with respect to Z, And that would be what that del vector is. So in other words, del is equal to I hat partial with respect to x plus j hat partial with respect to y plus k hat partial with respect to z. So you can see if you actually took the derivative of, let's say, mgh plus 82,000, if you take the derivative of that with respect to h, you're just going to get mg, right? So that 82,000 isn't going to matter at all. In fact, that's a truism about potential functions. You can add any constant to it that you want, because all that really matters is the difference or the change in the potential. See how we have that delta there? So if I had plus 86,400, I'd also have minus 86,400 because the delta is final minus initial. So what that allows us to do is when we're solving problems, I can call this height right here h equals 0, meaning the potential energy is going to be 0 there. I can do that anywhere. In fact, if I was, for instance, solving a roller coaster problem, right? And they said this point right here was 700 meters high. I don't have to care about that at all. I can say that's the lowest point. U is going to equal 0 there. So I don't have to carry that mg times 700 with everything, because that's just equivalent to adding a constant. So if they give you, say, the velocity here, and they want to know what the velocity is here, you're just going to say work in is 0 plus mgh plus 0 for the kinetic energy is equal to work out, which is 0, plus u final, which is 0, plus 1/2 mv squared. All you have to know is what's the height difference from here to here. Maybe that's 200.0 meters. And that's all you need. Notice in that case, you get mgh is equal to 1/2 mv squared. You don't even need the mass. That tells you that v is going to equal the square root of 2gh if it had no initial velocity. If it actually had initial velocity like I drew here, then I'd say v is going to equal the square root of v squared plus 2gh, which looks a lot like our kinematic equations, doesn't it? Okay, so that's sort of the background. Now you can just look at the book examples and that'll be nice, but I'm going to work a nice conceptual example, because physics is a couple things going on here when you're taking the calculus-based physics. And a lot of teachers, quote unquote, administrators will tell you that the calculus-based physics course is a weed out course for a lot of groups. Well, in a community college system, we don't believe in a weed out course. Okay, we know that that's the way people are using it, but it's not something that as a community college teacher I would ever want to have. Okay, I want you to learn stuff, and I'm going to do whatever I can to make sure you can get through the class and learn the material so that you can succeed. So a lot of this course is really about learning physical principles, and then about learning mathematical techniques to solve physics problems using those physical principles. And then another part is really about, are you knowledgeable enough about your mathematics, confident enough about yourself, good enough at your problem solving skills where you can survive a calculus-based physics class? Okay, that's why, unless a doctor happens to be going into, let's say, orthopedics, or if he wants to be an osteopath where they really highly specialize in bones and structures and stuff like that, they really are the mechanical end of the medical profession. If you're going to be a doctor of internal medicine, you're probably more interested in a really good biochem course after a really good organic chemistry course, and maybe some molecular biology and stuff like that. But the physics isn't necessarily needed. Again, that's what I mean. Medical school says, hey, if you're not good enough to make it through a calculus-based physics class, even if that's not your major, we don't want you here because you're really just going to be a waste of time for us. That doesn't mean it has to be so. But anyways, with that in mind, what I'm going to do is show you a physical principle that will come in kind of handy in terms of conceptual questions and stuff like that, and make you a little bit better educated as a physicist. So let's look at an example very much like the one that's in your book. Basically, you imagine two slides, one like this, and then one that's going to go like this. Okay. Now they both go and end at the same height right there. I'll call this path A and I'll call this path B. And what I'm going to say is the length is oddly enough exactly the same. So length of A is equal to length of B. Okay, that allows us to make life a little simpler when we're doing this. And I'm going to make this a little better than what I drew it here. So okay, so first off, I want to know the person on path A, when they get to the bottom, V final, is V final A greater than, less than, or equal to V final B? No air resistance, no friction. Anyone?
I say less than.
Okay. So if we look at our potential energy, our conservation of energy equation, again, I'll use my version. Work in plus U initial plus K initial is equal to work out plus U final plus K final plus E loss. I said there's no friction and air resistance, so that's going to be 0. I don't see any springs or anything, so those are going to be 0. I'm not saying anybody's giving a push, so those are going to be 0. And in fact, we're going to start from rest, so the initial kinetic energy will be 0. And in fact, I'm going to call this U equals 0 because I can, right? So initially, U initial is whatever that is there. So ultimately, all this equation gives me is U initial is equal to kinetic energy final. They started at the same time, they started at the same location, they started at the same height, but they took two different paths. So now would you say A is slower than B or B is slower than A, or they're equal?
Equal.
Yep. That means V final A is actually equal to V final B, because the whole thing driving the motion is potential energy being converted to kinetic energy. Since they started at the same height, they had the same potential energy. And since they end at the same height, they're going to have the same final potential energy. So all the energy they have left is kinetic energy, and that has to be equal to each other. So that's the first part. Now, the second part is which one would win the race, assuming they're racing each other?
B.
B? That
Yeah.
seems like it because it looks like a shorter path, doesn't it?
Mm-hmm.
But the problem is I've stipulated, even though it looks like it's physically impossible to be this way on here, but there are ways you could make it. I stipulated that the path lengths are the same. Now, what do you think's happening? Would they get there at the same time, or would A make it first?
The same time.
Okay, so watch what happens if this person's here and this person's here. This one has a really large U, but it has a very small K. This one, on the other hand, has a very large K, but a very small U. right? Since this person on A is consistently lower than the person on B, the person on A is going to be going faster at every point. So A is faster at every point on the path, on the slide, because A is lower than B, which means UA is smaller than UB, which means KA is greater than KB. So whatever the velocity is, it's at each point faster for A than it is for B. And since they're going the same distance, clearly A is going to make it first. So A wins. Your book does an example just like this, explains it in paragraph form. So you can look at it if my explanation so far doesn't make sense, or if you forget it and try to figure it out later, you can always look at the example in your book to get that. So does anybody have any questions on that one? Okay, so let's try a couple problems. We've learned a little bit of stuff about how to use potential energy and stuff of that sort, and kinetic energy. So let's say we have a roller coaster. I'm going to try another problem. So example. Let's say we have a roller coaster that's going like this, and then it comes like this, and then goes down like that. Let's say this height right here is 5 meters. Let's say this height right here is 20.0 meters. And actually, let me go ahead and make this with more sig figs. So I'm going to say this is 5.00 meters. And let's say that this height right here is in fact 30.0 meters. Let's say we have a car, roller coaster car, whose mass is equal to 1,000 kilograms because it's, heavily loaded, got a buttload of people on it. And let's say its initial speed is V equal 5.00 meters per second. Okay. So A, will the car make it over the first hump? If so, how fast? Meaning how fast they're going. If not, what speed is needed? Okay, so there's part A. So what we have again is work in plus U initial plus kinetic energy initial equals work out plus U final plus kinetic energy final plus E loss. I'm going to ignore friction on all of this stuff. And I'm not compressing any springs or working against friction or anything like that. So all these terms are going to be 0. Okay. And in fact, what when I get to the bottom, this area down here where everything bottoms out, that's going to be where I call U equals 0. So I'm not going to call U equals 0 in any part here, but for part A, I'm going to say that 1,000 kilograms times 9.80 meters per second every second times my height there is 20 meters plus 1/2 times 1,000 kilograms times 5.00 meters per second squared. Okay, I should have wrote that a little bigger so I can include the units. Okay, and that's going to be equal to M, which is 1,000 kilograms. So let me do it this way. That's going to be equal to 1,000. I'm going to leave off the units, 9.8 times H. In other words, that'll just tell me if it's really fast enough to make it the additional 10 meters. In other words, H less than 10 implies doesn't make it. Does that make sense? If the H is less than 10, it doesn't make it.
Yeah.
So let's solve for H. I'm going to say H is in fact equal to 1,000 times 9.8 would be 9,800 times 20. Grab the wrong calculator. That's going to be 196,000. Ooh, it's bigger than that. It's 1.96 million. Whoa, Nelly. Joules. Nope, I was right the first time. Dang it. Feel free to check my calculations here because you can tell I'm a babbling idiot. So it's 196,000 joules. That's that first term. 0.5 times 1,000 times 5 squared. That gives me 12,500. This is not looking good. But this is going to, and actually, since I made the 0 down at the bottom, H can't be 10. Anybody knows what H should be to make it make it? How high does it have to make it? I'm already at a height of 20 meters. So I was pretending like I was treating this as U equals 0, but U equals 0 is not there. U equals 0 is actually down here, right? So I actually have to say greater than 40. I think you can see already that that's not going to be the case because I'm now going to have to take and add those two and then divide by 1,000 times 9.80. And we'll get 208,500 joules over M times G. That would be a Newton. So 9,800 newtons. And that gives me 21.27 meters. So not nearly enough, right? Sorry, I misled you with my data about the 10. I forgot I had already called the potential energy 0 at the bottom. Okay, so it's not fast enough. So what I'd really like to do is now I have to do the same thing where I'm going to have that first number, 196,000 joules plus 1/2 M All right, let's do it this way. Go ahead and put in the number. Let's say plus 1/2 of 1,000 kilograms times v squared is equal to, I want it to just make it to the top. So the velocity at that end should be 0, but the potential energy should be 1,000 kilograms times 9.80 meters per second times 40.0 meters. And that can allow me to solve for V. So I'm going to say 1,000 times 9.8 times 40 is equal to 392,000. So I'm going to say 392,000 joules minus 196, excuse me, 196,000 joules over 500 kilograms. And then I'm going to take the square root of that.
I have a question.
Yes.
I'm confused on where the 40 meters came from.
So if you look in the diagram here, oh, wait a second. I thought I'd written 40 here, but no, I had written 30. So good question. You caught me for making an error. I probably remembered what I did earlier in class today.
Okay, I didn't mean to. I was just trying to figure out where the 40 came from.
That's good. That's the best thing that can happen. No, it's exactly what I want you guys to do. So thank you for that. Okay, so now I have a slightly different number than, well, so that. So instead of the 392,000 joules, I'm going to have to change that to 1,000 times 9.8 times 30, and that gives me 294,000 joules. So nice catch, dude. Appreciate it. So 294,000 joules minus 196,000 gives me 98,000. Joules over 500 kilograms. That turns out to be meters squared per second squared under the square root. So I'll say 196. Holy crap. Oh, I got to take the square root of that. Okay. So V for this one's going to be 14 meters per second. So it's got to be going at least 40 to make it over the hump. Or excuse me, at least 14 to make it over the hump. And that 14 is roughly what, 28 plus 7, be about 35 miles per hour. Okay. So now I've got a minimum speed. So part B, assuming V initial is equal to, let's say, 15.0 meters per second instead of 5.00 meters per second. What will be the speed at the top of the second hump and at the bottom? At the top of second hump. Oh, evidently you spell hump with an M now. And at the lowest point. Okay. So now I've got, again, work in plus U initial plus kinetic energy initial equals work out plus potential energy final plus kinetic energy final plus E loss. Again, we're ignoring air resistance and friction, and compressing any springs isn't going to happen. So all those are 0. I know the initial potential energy is 196,000 joules, because that's the same thing we calculated earlier. Now I have plus 1/2 of 1,000 kilograms times 15.0 meters per second squared. And at first hump, which is what I'm doing here. Okay, so you can see I'm doing first hump here. I don't know what I just did. Stop, go back here. Oh, what happened to me? Ugh. Okay, something bad has happened here. There it is. Woo, scary. Okay. That's going to be equal to 1,000. I'm going to leave off the units since we're tight on space. 9.80. And now if I look at my original diagram, the first hump right here has a height of 5 meters. Okay, so that's what I'm going to use. Plus 1/2 1,000 times V squared. Okay. So I have 196,000. I don't like this red. I have 196,000 joules plus 500 times 225. Wrong calculator again. That's equal to 112,500. And this is equal to 1,000 times 9.8 be 9,800 kilogram meter per second squared times, actually I might as well multiply that by 4, or excuse me, by 5. Stupid me. I was thinking that was the kinetic energy term. So I'm going to take that 1,000 times 9.8 times 5, and that's going to give me 49,000. I'm going to use my pen instead of my calculator. And that's going to be equal to 500 kilograms times V first squared. So I take the 196,000, that is 196,000 plus 112,500. Now subtract from that 49,000. And that gives me 259,500 joules divided by 500 kilograms. Take the square root of all that, and that's equal to V first. In other words, the velocity at the first hump. So that divided by 500. That's 519. Take the square root of 519. Meters squared per second squared. And that gives me 22.78 meters per second. So that's the velocity at the first hump. That's pretty darn fast, right? That's roughly 2.5 times that. So that's 44 plus 11, 50, 55, 56, something. So about 56 miles per hour. That's pretty fast. Now they want to know what is it at the lowest point. Well, the same thing happens here, except now you have, so lowest point. We're going to have, again, 196,000. Everybody knows where this 196,000 is coming from, right? Plus 112,500 joules. That's the same kinetic energy that we had initially. Now plus 0 or equals 0, because of potential energy at the very bottom right here is 0, plus 1/2 times, not 500, but 1,000, times V bottom squared. So I'll put a VB there. So V bottom is equal to the square root of 196,000 plus 112,500. That gives me 308,500 joules divided by 500 kilograms square root. That gives me the square root of 617 meters squared per second squared. Which is the square root of 617 is 24.84. And of course, that's got one extra sig fig, that's got one extra sig fig, and that's it. So any questions on that?
Can you just cut back to where the 196 was calculated again?
Okay, where the 196,000 came from?
Yeah.
That is supposed to be, assuming I did my math right now, and that's a big if, that was supposed to come from right there where it says H equals. If you multiply 1,000 times 9.8 times 20, which is the height it is right here, right? Then 1,000 times 9.8 times 20 should give you the 196,000.
Okay, I got it.
Okay. So just to recap what we did, I was sort of running on the fly, making up a problem in real time, but we had a cart that I just drew as a single cart, obviously with a roller coaster, it'd probably be several cars, but the main thing is it had a mass of 1,000 kilograms, and I initially said it was moving 5 meters per second. I wasn't sure, I was pretty confident it wasn't going to make it, in fact, but I was pretty sure it wasn't going to have enough speed. So I first said, will the car make it over the first hump? And if so, how fast will it be going? If not, what speed is needed for it to make it over the hump? So I first calculated what would the height be. And since I had made this point right here, U equals 0, that means my height here is 20 meters. And my height here, of course, is 30 meters, even though I tried to make it 40 for some ungodly reason. Okay. So I just calculated what H would be and only got 21.27. In other words, it's literally going to make it 1.7 meters up. So that was what was going to happen if I left it at 5 meters per second. So then the other part, after I said it's not fast enough, I said, okay, well, let's let it reach a velocity of 0 right there at the top. Okay. And that's what I'm doing here. I said, I have initial potential energy of 196,000, plus I have initial kinetic energy of 1/2 times the mass times V squared, which I'm trying to find, the V. And I want it to be equal to 1,000 times 9.8 times 30, because then it would be fast enough to just reach the top. In solving for that, I found the answer was 14.0 meters per second is how fast it had to go to make it over the hump. So then in part B, I said, let's assume it's actually going 15. So it'd have a little bit of extra speed in case, you know, you really did have a friction coefficient. There would be a problem. In reality, you're always going to have some friction, but you'd have to figure out what that friction is and or at least deal with it. So I said, heck, I'll just bump it up to 15. Now I then asked, how fast will it be going when it reaches the top of the first hump, which is this thing, or excuse me, second hump, and then how fast when it reaches the bottom, which is that thing right there. So in doing the first hump, I just did 196,000 joules for the initial height. I did 1/2 times the mass times 15 meters per second squared for the kinetic energy. And then I said the final kinetic potential energy be 1,000 times 9.8 times 5 meters, because that's how high that little part right there was just 5 meters. So the hump, the second hump, was only 5 meters high. And I said that's going to be added to it, a kinetic energy equal to 1/2 times 1,000 times the final velocity at the first hump squared. And that's what I'm showing here. Okay. When I solved for that, I got 22.78 meters per second. That's pretty darn fast. I carried one extra sig fig as far as I can tell. Then I asked, well, what would the velocity be at the final one? And by doing this, I was allowing you to see that, yeah, guess what? The same problem might have U final equals 0 in one part and U final not being equal to 0 in another part. That's the whole reason why I actually did a little bit extra from what the book's example had. So again, I started with 196,000 joules. That's just being 20 meters up, plus 112,500 joules, which is the kinetic energy it has from going 15 meters per second. And that's equal to 0 potential energy plus the kinetic energy that it'll have at the bottom, which is 1/2 times the mass of the cart times the V at the bottom squared. Solve for V at the bottom, I got 24.84. Any questions on that? All right, so we've basically now covered all of chapter 8. I'm going to get you started just a little bit because we're at 7:15, 7:16 right now. We're supposed to go to 7:50. I can do a little bit of time on chapter 9, and that might actually allow us to get off a little bit earlier from chapter 9 next time. So I'm going to go ahead and go into chapter 9 unless someone has any questions on how this was worked or any past stuff. Anyone? All right, so that equation you can use over and over again, the work in plus U initial plus U K final plus work out plus U final plus K final plus E loss. And you can write it on your equation sheet, even though it's not an equation that you'll find in the book. I don't mind that one being written on there. But you might actually find that you prefer to just use the way the book does. That's fine too. I'm not going to be looking at your work to see whether you're using exactly my technique. All I care about is your ability to get the right answer. I've just found over time that that way of writing that equation can allow us to do a bunch of different problems that you otherwise can't. I mean, sometimes they'll say problems like, let's say a car is moving at 60 meters per second and it starts to make it up a hill. How far will it get if it's going to lose 80% of its energy to friction? So all you have initially is a 0 potential energy plus the kinetic energy equal to 1/2 m times the velocity squared. And that's equal to just the U final, which would be mg times the h that you want. Notice both terms have an m in it, but because we're losing energy, you'd have to put 0.8 times the 1/2 kx or 1/2 mv squared would have to go in the E loss term. Or you could go in the work out term. Either one of those would be fine. But by having that extra work out term and that E loss term, I can use either one of those to account for the energy loss. So your book literally does problems like that, but it just gives you equations like delta U plus delta K is equal to 0. So you've got to play a little extra trick to pull that off. That's why I like to write it the other way. So does anybody have any questions on that before we go into chapter 9? Okay. So I'm trying to stop my share of my screen, and I cannot do that for some reason. My little thing's gone. Where'd it go? Maybe it's back here. Oh yeah, I know where it is. Nope, not there. Nope, not there. Oh, let's try this. Nope, that's not helpful either. That's not helpful either. I do not want Chrome running. I want my Zoom running, dude. That's not helpful. That's not helpful. Not helpful. Not helpful. Not helpful. Okay, so somehow I just lost my screen. Oh, there it is. I found it. Okay. Sorry about that, guys. It's so nice that they hired the elderly to teach this class. So what I'm going to do now is share a different screen so we can jump into chapter 9. So let's do this one. And what I'm going to do is take you to this page. This is your textbook. So what I was talking about earlier about where you can find the constants, I'm going to go ahead and show you that. Right here where it says in papers, this is actually what's in the front cover of a hard book. So if you actually have a hardcover book, you would have this in the inside of the front cover. And you can see it's pretty helpful. It's got all these constants: mass of a proton, mass of an electron, mass of a neutron, all that good stuff. It's got what the atomic mass unit is. It's got the mean radius of the Earth, the mass of the Earth, the mean radius of the sun, moon, the mass of the moon, the mean radius of the sun, the mass of the sun. You can see also, oh, I went to page 3 by accident. Okay. Or maybe I didn't. Okay, so yeah, okay, I see it now. So in paper 2 seems to be a blank sheet. So that's how, oh good, no, it's not. Okay, here's a bunch of conversion factors and the SI prefixes. So you can see it does in fact go past tera and peta. It actually goes to exa, zeta, and iota. That's nice. It also goes to past femto. It goes femto, atto, zepto, yocto. And you can see all various units and stuff like that. You can go over here and you should see some math identities. Binomial expansion we use a lot, for instance. You could, for instance, say if you really want to do a nice job on that extra credit problem with Newton's law of gravity, down in the bottom where it has r squared, you can treat that as the radius of the Earth plus or minus the small distance that you're doing, which would be the altitude of Mount Everest would be the plus, or the depth of this Marianas Trench would be the minus. And then you could put a 2 here. But what you do is factor out an r squared first. So that would leave a 1 plus or minus r over little r. I mean, little r over big R. So that little r would then be appearing here, and you could actually get a little bit nicer expression so you can get it exactly, you know, what decimal place it's off by. But anyways, that's a binomial expansion. That's something we use a lot. Quadratic formula. There's the formulas that we'll use for spheres and rectangular solids and some trig identities. And I think we got one more page that, oh yeah, that's the periodic table. So all that stuff's on there. And these masses, by the way, are those atomic mass units, but I also treat them as 12.017 grams per mole. That's another way of looking at it. All right, now back to what I was actually going for, which is chapter 9, linear momentum. So this is a chapter on linear momentum, and this is where you can actually start studying collisions, because collisions can be kind of messy. The forces that occur between, you know, 2 cars colliding are not conservative forces. You can tell because, for instance, when a car, even at a slow speed, hits another car, there's going to be some fiberglass or plastic or steel or aluminum or something that's going to be crumpled. And that takes some energy to squish it. And some of that energy goes into squishing it. And in fact, the metal will get hotter. And if it's plastic, it'll take some energy to break it as well, or fiberglass or whatever. But also you're going to hear sound. So some of the energy is going to be lost to sound and heat and all that good stuff. So these forces of collision are often not cool with conservation of energy. So we have to reassess how we're going to do it. And it turns out when Newton wrote his Principia, he didn't really write F equals ma. That was a later version that you can use. He defined a quantity, mass times velocity, which is the momentum. Notice that's a vector. See, you got a P there with a vector symbol over it and a V with a vector symbol over it. So you can tell already that since mass is always positive, clearly the momentum and the velocity will be parallel to each other, because when you multiply a scalar by a vector, it only changes direction if the scalar is a negative. So we got that. And then if you look what Newton wrote that the total force acting on a system is equal to the instantaneous rate of change of momentum, dp dt. Okay. Now, if you had the special case where the mass was a constant, then that P equals mv could allow the m to go right through the derivative, and then you get m times dv dt. That's what ma is. Okay. So with that in mind, we're going to go ahead and work physics in terms of that. So you can, for instance, if you, just like we did when we did distance divided by time for average velocity, you can say average momentum change, which would be the average force, is just the change in momentum divided by the change in time. And here, I think that's one of our American tennis players. His name escapes me right now, but anyways, I can't remember his name. I haven't watched tennis in so long, I forgot. But anyways, for a top player, a tennis ball may leave the racket on serve with a speed of 55 meters per second, which is about 120 miles per hour. I've actually seen Venus and Serena Williams kick it at 120 miles per hour. In fact, quite a bit higher. And I've even seen males now hitting at 139, 142, something like that. So that's really, really fast. But either way, what they say is if the ball has a mass of 0.060 kilograms and is in contact with the racket for about 4 milliseconds, that's pretty typical, estimate the average force on the ball. Well, what you're assuming here is the ball was essentially going zero, because chances are it's going to be going up anyways, not horizontally. And in fact, it's kind of weird to think about this, but it's a matter of fact that even if you're 7'8", okay, you cannot hit fast enough the ball to actually hit it downward and have it go over the net. So you actually have to hit a little bit upward, even if you don't think you are. You're hitting a little bit upward. But the main thing is the initial velocity would be zero. So mass times initial velocity would be zero. The mass times the final velocity would be 0.060 times 55 meters per second. And you divide that by the 0.004 seconds. That's 800 newtons is what you get. And that's basically larger than the weight of a 60 kilogram person. Okay, a 60 kilogram person, which would be like a fourth grader probably. Fourth grader, well, actually, I guess you could say that's 2.2, so that'd be 120. That could actually be a freshman, you know, probably not on the football team unless he's a wide receiver or kicker or something. But anyways, that's about how much force you have to have. So even though that tennis doesn't seem quite as scary as getting hit by a baseball bat, a tennis racket could jack you up pretty well. Okay, so that's a typical problem we'll solve. You can also do it for what's the momentum change when you're spraying your car to wash it. So that's another example your book does here. Another thing you can do is you can go back to this original equation and say the total force is equal to dp dt. You could actually integrate both sides, first multiplying by dt, and then integrate both sides. And what you get is the integral of the total force dt is equal to the change in momentum. And both of those quantities, the integral of f times dt and the change in momentum, are called impulse. So that's another term we're learning. And I'm not going over any problems right now. I'm just trying to get you through some of the definitions we're going to be using. So that integral of f dt that I just talked about, and hopefully it'll show in a second, that's called the impulse, and that's IMPULSE. And the change in momentum, which is P final minus P initial, is also called the impulse. And I'm going to show you somewhere. They normally cover it in the first pages, but Giancoli didn't do that in this book. So here's collisions and impulse. So if you take the integral of f over the time period, that's going to give you the actual impulse. So that's what I was talking about, the integral of f dt. But because of what we did, the integral of f dt also happens to be equal to the impulse, which we give a symbol j, but that's just P final minus P initial. So those are the major terms we're talking about. There's another term too, when we talk about things colliding. If two cars collide, car one is putting a force on car two and car two is putting a force on car one. If you treat both cars as your system, then the only forces acting on the cars, or the major forces acting on the car, is the other car, but that's that's an internal force. So you don't actually have to take that into consideration. The only force that really is acting is the force due to the normal force of the earth holding up and the gravity pulling down on the cars. If these friction forces that happen due to the cars skidding or something, if they're considerably smaller than the collision forces, then you can essentially say that the net force acting on the system is zero, and you get something called conservation of momentum. See, delta P is equal to change in momentum. But if your net force acting on the system, in other words, you can still allow all the forces of car one acting on car two and car two acting on car one. The only forces you're ignoring is the weight, which gravity is pulling down with, the normal force, which is canceling out the weight. So those are automatically going to cancel out. And then you have the friction force. If that's fairly negligible, then you can say this integral right here is zero, and you get that the change in momentum is zero. That is the very definition of conservation of momentum. It's when the net force acting on a system is zero, then momentum is conserved. So if this is zero, you get dp/dt equals zero. What kind of function has its derivative equal to zero? Is it linear? Like f of x equals 3x plus 4? Would that have a derivative of zero? Anybody? Bueller? Okay, so if f of x is equal to 3x plus 4, then the derivative would be 3. So that's not zero. But what if f of x was just equal to 4? What would its derivative be? Anybody here? Okay, so we have dBdt, that's the instantaneous rate of change of momentum, is equal to the total external force acting on the system. And I said, if the total external force acting on the system is zero, which is sort of a approximation when you're dealing with car crashes, high-speed car crashes at least, then the derivative is equal to zero, and that means the momentum must be a constant. So that's all they're saying here. When the net external force on a system of objects is zero, the total momentum of the system remains constant. That's the conservation of momentum. If, however, you can also conserve kinetic energy, then that's called an elastic collision. So that's another terminology, another term you need to know. And in fact, if two things collide, sort of like train cars, they have this little clicking mechanism between them. So when two of them collide, they actually hook up and become attached to each other. In that sort of scenario where two things collide and stick together, that's called a perfectly inelastic collision. So that's all the real terminology you need for today. And I think I've got you a good start into momentum. I'm letting you go about 17 minutes early. I'm okay with that. You guys are free to go, but I'll wait for the last person to leave in case you have any questions. So thanks for coming, everybody. Hope y'all did well on your midterm today. And I'll let you know pretty soon when we're going to have another test. Probably I might have another online test. I'm not sure yet. See you, Nora.
I think you should do that.
You think I should
Yes.
do? Yeah, they help you a little bit, don't they?
I second that note.
I haven't looked at the grades yet, but I did see a couple of my daytime students that weren't happy. One said, I'm not completely sad about the grade I got, but it's not the grade that I was hoping I'd get. So
For the online or for this midterm?
that student said it for the midterm. They did theirs this morning or this afternoon at 12:45.
I would like
Oh
to
yeah, I know that.
motion about doing that second one online.
Okay, you would like that too, huh?
I
I probably will have at least 2 online tests, period, just because that helps your grade a little bit. But I want you guys to try to figure out what's going on. If you've been doing pretty well on your homeworks, meaning you're able to figure stuff out and don't have to use a lot of Chegg or a lot of looking up solutions or anything like that, but your test grades aren't that good, then I really want you to try to figure out how you can better learn. Maybe you are leaning too much on Chegg or solutions manuals or Shalm's outlines or stuff like that. And that's sort of the holy grail, is really figuring out how to learn. And each person has to do that in some way because each person has a pretty much a different way of learning. So work on that as well. But yeah, I will definitely give you at least one more online test. I'm not sure if it's going to be the next one or not, but we'll see. And I have heard your words of encouragement regarding that.
Do you know how many tests we have left, or how many tests we have left?
I think I had slated us to take like 6 tests.
Okay.
If you how did you do better on the first one? Because this is the second one we've had face to face. Hopefully that first one was a little better.
Yes, I did do better on my first exam.
Good deal. And so remember, that's going to go. And I'm also going to drop the one lowest. I think that's what I agreed to. So that'll help. And when we mix in I'm not counting them differently. Like normally I'd count all the online tests to maybe only count 15% or 10% of the course. And then the midterm and final, which would be face to face, they would count like 55% total. So I'm not doing that this time. I'm counting them. So maybe we will have a couple of online tests as opposed to just one. I'm sure we're going to have at least 2. Let's put it that way. Save me time too. Anybody else have any questions?
No. You have a good.
So
Go ahead, Courtney. You said me have a good time.
I said have a good rest of your evening.
You do. You too. Thank you, Courtney.
Thank you.
And who was the gentleman that was speaking next? Was that Samuel?
yeah, that's me.
Okay.
So I emailed Mr. Mitchell yesterday
Yeah, he told me.
because I've been sick for the past couple days, and he told me to message you and let you know. So
Yeah.
I don't know what I'm supposed to do in order to make up the test and the practice test and stuff like
You're
that.
not the one that came down with COVID, right?
No, I didn't test. So
Okay. So if you couldn't make it today, it's not a big deal. I can set you up to take it at the testing center. It'll be a slightly different test. So those of you who've already taken it, you don't want to share what was on the test with anybody else because they might not have taken it, and you give them a curve breaking high grade. You think you could take it tomorrow or maybe the next day?
it would probably have to be the next day because I would already be in Virginia.
Okay. I tell you what, send me an email tomorrow to remind me, and I'll set up a testing center test for you tomorrow.
Okay, thank you.
I mean, yeah, I'll set it up tomorrow, but it'll be for the next day.
Okay.
All right.
Sounds
Thanks,
good.
Samuel.
Mhm.
Isabella, Josiah, anybody have any questions?
Oh, one more thing. Could you open up the practice test for me so I could
Yes.
keep doing? Okay.
Were
thank
you the one that asked earlier, or there was somebody else that asked as well, wasn't it?
I think that was cast on.
Casting, that's it. Yeah, cool. All right, I'll get both of y'all on that.
All right, thank you.
Have a good one, folks. Josiah, did you have a question before you go, bud? All right, well, have a good one, everybody. Nice seeing you tonight. Bye-bye.